Welcome everybody. It's lovely to see so many joining us today. Water modelling using HEC-RAS 1D and 2D. We have three internationally respected HEC-RAS mentors, Krey, Mark and Bob, and we'll introduce them in a moment. But hi, I'm Trevor Pillar. I'm the National Partnerships Manager. You can see the countries they're coming from right across the globe, and we're glad you've been able to join us. Today's presenters, these three gentlemen, are authors, educators, users, practitioners at a high level. Mark, Rob Keller and Krey Price. I'm going to hand right now over to Krey and we'll get this thing started, and I look forward to what we're going to hear from you. Thanks, Krey.
Great. Thanks, Trevor. Hopefully everybody can hear me okay. I'd like to start with a brief introduction of HEC-RAS, and we are going to breeze through just one topic each for the presenters so that we can focus most of our time on your questions, because that's really what we want to do here, is make this interactive. Looks like we're coming from a wide background of different geographic areas, probably also a wide background of different abilities and capabilities of 2D modeling and 1D modeling. And we'll talk about some of these interfaces and some of the cool features of HEC-RAS as we go through the next 45 minutes. I will just briefly introduce HEC-RAS 5.0 as a new software program that has incorporated two-dimensional hydrodynamic flow routing. Now, those of you who have used 1D before are going to be very familiar with the interfaces, but we are still able to use the 1D models, coupling them to 2D models, or use pure 2D models. And there are a couple of exciting features about HEC-RAS that allow you to use the subgrid bathymetry and the subgrid resolution of the LiDAR data, which set it aside and set it apart from some of the other 2D modeling packages out there. Mark will be talking about some of those, and Bob will be talking about some of the 1D and 2D solutions and how to get structures into your model. Before we get started with that, though, I wanted to just go all the way back to the beginning, start from scratch. So Joel, if you can move on to the next slide. I'll show you what we've got here now in RAS Mapper. This is a new button that you wouldn't have had with the previous versions of HEC-RAS. It is a GIS program. It's a GIS interface that works similar to any other GIS program, where you can stack layers up and view them. Now, before we do anything in RAS Mapper, we have to tell HEC-RAS where on the globe you are. Now, you may be familiar with this already, and I'll step through a few of these just from scratch to let you know how you would go about doing this if you had nothing but a computer and Google. You had nothing else. I've got a workshop for download on our website, surfacewater.biz. That workshop's available to step you through from the very beginning. And these are some slides that are excerpts from this. Before you start, like I said, you have to go in and tell it where in the world you are. That's the projection file, an Esri format projection file. On the next screen, I'll show you where you can grab those. Spatialreference.org has free downloads of PRJ files for basically any projection you would ever want. On the next slide, you'll see then a free database. This is for Australia. I thought we'd have mostly Australian visitors here, but because we're all across the globe, you might have your own country's data sources available to you. This is one particular slide showing free downloadable digital elevation model data. And this is available in Australia from the ELVIS network. ELVIS is kind of a funny name, but it's the Elevation Information Service or System. And that's available at anywhere from 5-meter resolution to 30-meter resolution digital elevation model raster grid formats. Go on to the next slide. You'll see what that looks like for Australia, and there are similar interfaces elsewhere on the planet. If I go on this one and I click extract, I can go to the next slide and show you where we would go ahead and grab some data for Australia. A very relevant set of flood maps and flood modeling data in Australia is the Brisbane River. So I've just zoomed in on that one just for an example. I go and drag across my box. And once I click on that, I have to set my PRJ file and go ahead and recognize where that is. And then on the next slide, you'll see how the interface works, where you go ahead and take the downloaded file that it has just emailed to you, and you can go into RAS Mapper, create a new terrain, hit the Add button, and then you can pick any number of formats. Now, keep in mind, in HEC-RAS, it's initially only going to give you 3 data formats, file formats: TIFF, float files, and ADF files in Esri format. But if you drag down, as you can see in the lower right, for any sort of raster data, I think there are 60 or 70 different formats that it can actually work with. In the end, what you need, and I'll show you this, and I'm not sure if it'll come through on my slides, hold it up nice and close to my screen here. You see one of these kids' toys. this is what it looks like. If you have elevation data that's in a raster grid format, you have got one Z elevation for every single X and Y coordinate. That's what we need. We need raster grid data, not vector data, not point-to-point data. We need every single grid covered. If you've got data in that format, you really can work with pretty much any format on the planet that's available and pull this into HEC-RAS, into RAS Mapper. And I'll show you what it looks like when we pull that set up that I just downloaded off of the Brisbane server. Go ahead and pull that to the next slide. You can see the raster information in the background that's color-coded. Now I can mess around with all of the color coding and the elevation ranges, much like you can in any GIS software. Go on to the next slide and we'll see what we can do now with Google Earth and with Bing imagery. One exciting feature is if you're in the right place on the planet, and this is a good way to check your model, find out if you're in the right place before you do anything else, click on Google Satellite or Bing Satellites and you add those. On the next slide, you'll see what happens. It'll overlay it on top of your raster image, but you're not going to be able to see your raster image down below it, your terrain data, until you make it a bit transparent. And I like to balance this a bit so that I can see terrain data, see where I'm at elevation-wise, and also see the buildings and the bridges and the rivers underneath it. So on the next slide, you'll see a merged set of data where you're able to see the buildings underneath, but still discern the catchment boundaries and the things that you're going to need to pick up elevation-wise. Now we can go chop this any number of ways. In the workshop, if you download that from surfacewater.biz, you'll see some additional features that you can do, cutting different profiles across this terrain to try and interrogate it before you go setting up your computational grid. Once you've done that, and Mark's going to tell us a little bit more about that, you can then come back into RAS Mapper after you've run your model, and I'll just show you a brief slide on that one in the next slide, where you can come back in and interrogate your model, and you can plot velocities and water surface elevations. And this is a very coarse grid model, as you can see, but it does a fine job in at least routing the flows in the right direction and showing you where that goes. Now, what we're going to do now, when we move into Mark's portion, again, I'm not sure if you can see these little gimmicks that I bring along to the course. This is a brownie pan, my wife's brownie pan. What we're going to do now is take this underlying LiDAR resolution data, which can be at a really fine resolution, sometimes 5 centimeter or 50 centimeter pixel resolution accuracy. So we've got that subgrid bathymetry as LiDAR data, as DEM data, underneath this computational mesh. Now what Mark's going to talk about is taking our computational mesh and we're going to overlay it. We're going to squash these brownies down and we're going to be able to interrogate the subgrid bathymetry and put our model on top of it. So with that, again, we go through a lot more of these exercises in our course. We're going to actually talk about in RAS Mapper how to take any 1D model, any shape you can make in a 1D cross section and cut it through, like civil design software, through the terrain data. And once we do that, you can make any shape you want out of your terrain data. You can manipulate it, you can put in building pads, levees, dams. You can actually build your terrain data any way you'd like to see it and get very creative. So we do that in the course. We don't have time to step you through that here, but there are some really exciting features and it's actually very easy to use. And so, but before we get into seeing some of the cool results and animations, Mark is going to show us now why the subgrid level of bathymetry is important and how it sets HEC-RAS apart from other software. Thanks.
Thanks, Krey. Those of you who've used two-dimensional models in the past understand oftentimes you have to grid your terrain, your mesh to a level of detail that's going to capture the terrain features. What you see in this slide is in the lower left is a representation of a TIN, a triangular regular network of a terrain surface. Capturing that detail at that level within your model requires that you mesh it fairly finely. What you see in the upper middle quadrant of the slide is how some 2D models, most 2D models that are triangular meshes would see that terrain surface. Each of the grid elements is treated as a single elevation. The lower right is a rectangular gridded model where it's again seeing that the terrain with a single elevation, so it sees the world as a series of stair steps. So the terrain is extremely important to capturing terrain detail, and then the finer you mesh it, the more of that terrain detail you're going to see in your model. But the finer you mesh it, also the longer the runtime of that simulation will be. So if you skip to the next slide, how is RAS different? The computational mesh at the subgrid level of detail is extremely important to how it sees the terrain. And what RAS is seeing is that image in the middle. where each of the edges of the cell are actually a cross section where hydraulic property tables are extracted. The center of the cell is treated as a stage storage relationship, and what in that instance the model can see is that flow entering at the face closest to you would exit out of the face farthest from you first before it would begin to interact with the left and the right sides. The water would have to get deep enough in that cell for it to know that it can interact with those adjoining sides. And that's a unique difference compared to other two-dimensional models. And so obviously the more accurate your terrain is, the more of that detail it's going to capture. So if we go to the next slide, we'll show you an example. This particular example is the Mississippi River flooding during the 2011 event. That's the Ohio-Mississippi River confluence in the United States. During this event, several of the communities were beginning to flood, and the Corps needed to look at an alternative that would alleviate that flooding by blowing up the levees in that area in the center where you see that orange outline is an area that's protected by a levee, and they actually dynamited the levee at the north end and the south end to allow water to escape into that interior area. So what you'll see in the simulation is that level, that importance of that subgrid level of detail in the simulation. Is it running? So we might need to advance it. There we go. So you see that water progressing up through the smaller channels in the domain. They're going to progress over to the right-hand side and then begin to expand out into the floodplain, as well as another pathway there in the center that will push up into that upper center quadrant. Most two-dimensional models are not going to see that progression of the water into the domain unless you gridded it at a very fine detail. There's the RAS grids. So you can see that those channels are subgrid level, but RAS is capable of picking up that dynamic at the subgrid level and propagate those flows out into the floodplain correctly by being able to see that subgrid level of detail. This was used as a validation of the early version of the HEC-RAS 2D code in 2011. So they also installed temporary gauges to capture the event and compare those against the simulation with great success. It was very close. The results were very close to the simulated version of the particular exercise. So one of the things that's key is because of the fact that RAS sees subgrid level of detail and the hydraulics are done at the grid face, it's important to align the grid face to the features in the terrain that are going to control flow behaviors, as you'll see in that simulation in the lower left-hand corner. That linear feature across the domain has to be captured in the grid face. You do that with break lines, which allows you to refine your mesh that starts out as a simple rectangular pattern, but RAS is capable of using an unstructured mesh that can have up to 8 sides to each grid cell. So you can see the refinement of the mesh around those features allows it to see those features correctly and properly route flow around those features until it gets deep enough to overtop them. With that, I think we pass that to Robert.
Thank you, Mark. As I look at the poll results, I can see that a large number of people have used the 1D steady flow with lesser numbers down through the unsteady, 1D, 2D coupled, 2D by itself, and scour and sediment transport. So that's very good to see, because one of the real issues that we have is that a lot of the modelling of structures which is developed within the 1D version of HEC-RAS is currently not available in the 2D version. And the slide that you're looking at there with the drop-down menu for structure type shows that really there are only those 4 different types that are available at this stage. And a notable omission is bridges, which feature, of course, in an awful lot of the terrain modelling and the flood modelling that we do. I just want to talk about bridges briefly, because there are 1 or 2 ways in which, well, we can model the effect of bridges within 2D modelling, and then I'll make a couple of comments after that. So on the next slide, so I've made the point that modelling hydraulic structures is very limited in RAS 2D. There are some options that can be used for adding a bridge, and I would emphasise that what we're talking about here is just a very simplified, just a very small part of what will be in the course in September. It is possible to add a bridge simply by modifying the terrain model to include the bridge embankments, the piers, and the abutments, and this can be done. Now, that's easy to set up for existing bridges that are included as part of the terrain. It does require you to manually edit the terrain to model the proposed bridge. And more importantly, it can only simulate low flow through the bridge. You can't have any impact with the bridge deck itself. And if it's not possible to simulate complex shaped piers, it can only be done where you've got piers of a constant shape from top to bottom. Alternatively, a surface area 2D area connection with a culvert or a series of culverts can be used, and this is very useful for much wider bridges where the openings are relatively small. In this case, we could simulate a situation with box culverts where the distance between the culverts, the thickness of the terrain between the culverts, in fact, represents the pier heights itself, represents the piers themselves. It has the advantage of being able to include bridge overtopping and interaction with the bridge deck itself. Disadvantages are that the culvert equations are in fact used to model a bridge and not the multiple bridge routines which are available in the 1D version, and it may not be possible to get the culvert shape to perfectly match the bridge opening, and calibration because of these disadvantages would clearly be required. So I also want to emphasize the fact that within the 2D model, bridge scour cannot be modeled, and if we move to the next slide, I want to emphasize that scour at bridge sites remains the single most common reason for failure of bridges. And what we're seeing here is a bridge on a road in Tasmania where the flood has clearly made a mess of the bridge itself. The next slide shows the same site with the replacement bridge in place, and this is very clearly a much better structure for the conditions and shows a much better response. But the next slide is of the same bridge, and I've put this in just to emphasize the complexity of flow around bridge piers. And HEC-RAS 1D has well validated modules built in for both bridge scour, or for bridge scour, for abutment scour, and for constriction scour at bridge sites. And the complex shape that we see here for flow around the pier, where you've got the classic sort of drawdown around the front of the pier, the flow is from right to left, and the pressure gradient that's driven down the nose of the pier to create horseshoe vortices and so on. This is all modelled well in 1D, and indeed to model this kind of phenomenon you need to use HEC-RAS 1D. If scour is an issue, we must use 1D modelling, and other structures, irrigation controls, pump stations, many lateral structures, etc., etc. These need to be used, and 1D modelling is required for proper structure simulation. Now, I'm talking about bridges and indeed other structures itself. There is, I understand, a new version of HEC-RAS 2D coming out, which will enable the statement, or will enable us to introduce rating curves within the 2D domain itself at particular locations. And these rating curves, of course, can in themselves model structures where a 1D model of the structure has been used to generate a rating curve, which can then be put into the 2D model. That's as far as I want to go, just to emphasize that we need 1D models where we have significant structures, because the modeling components within the 2D model are currently not particularly extensive.
That's great. Thank you very much, Bob. That was excellent, and Mark before him, and firstly Krey. So that's excellent. We've got a few questions coming in, and a ton of listeners and viewers to this webinar. So we'll get straight into the Q&A session now. If you want to ask a question on screen, just raise your hand and we'll make sure that happens. type in a question in the Q&A. That's absolutely good. So we'll kick straight off, I think. Let's get cracking. Welcome, Wahid. I understand you're from, your mic's not on. Your mic is not on. Somebody's got to turn it on. Here it comes.
Yes.
That's it. And you're in Pakistan at some unearthly hour of the morning.
Yes, here is morning and
Welcome.
good afternoon.
Welcome.
To you all. Thank you. I would like to raise a question which is a multifold. That first pertaining to the use of digital elevation model in low relief terrains, typically in the deltic plains along the coastal areas. How we should start modeling in such cases when bathymetry is hard to discover. And the second one, let me explain another. As in case of 1D modeling, we often use discharge or water level as at the gauging stations for calibration. What parameters we should use while using 2D model, because it is more sensitive and more accurate. So regarding which sort of the parameters we should use for calibration. And the last one, we calibrate our hydrodynamic models for alluvial rivers in such channels using one-time readings or maximum 2 times. But after every flood event, the morphology and alignment of the alluvial river changes. So what we should use while taking the long-term predictions using hydrodynamic model like HEC-RAS 1D or 2D. Thank you.
We just go. There's 3 questions there, and there's a lot in that. But thank you very much for your question, Wahid. That's absolutely brilliant. Let me just get that first question straight. The use of DEM in low relief terrains like deltaic plains along coasts. How should we start modelling in such cases when bathymetry is hard to discover? Who wants to kick off? Is that a Krey question?
I'm up for anybody wanting to ask that. What we would do if bathymetry is not available, you have to actually extract the bathymetry from your terrain data. And I've got an example in one of my workshops that I've just done, posted something on wormhole culverts on my website, where I've gone in and extracted some terrain from it. I've actually taken the bathymetry out. So you would need either manual readings, and you can do this with 1D cross sections. You can actually run a cross section from out in the delta and pull the water out of it by lowering your terrain. And it's a bit complex. Come to the class and you'll learn some more about it. If you're not able to come to the class, there's a blog called the HEC-RAS blog. Just Google the HEC-RAS blog and it'll walk you through a concept called terrain lifting. And that will show you exactly how to do it. And you just have to define it yourself. You define it manually. And then once you've defined it manually in 1D, then you can run that cross section any shape you like and pull the water out of it and lower your terrain to it. But probably much easier done in some civil design software than in HEC-RAS, but it can be done.
Yep, that sounds great. We're going to have to keep our questions short and answers short as well, and we'll highlight the fact that in Brisbane in September there is a 5-day course, and we'll deal with all these things in much more detail. But shall we go to the second question from Wahid? In the case of 1D modelling, did we get onto this? We often use discharge or water levels at gauging stations for calibration. What parameters should be used while using 2D model?
Well, I'll pick up that one. It's the same as with a 1D model. You're going to use all the available data you have, which would be extensive flooding that you might have from the event, from aerial photography, but that gauge data is going to be key as well. All available data that you're going to use for a 1D model would also be used in a 2D model. You can query your results at that gauge location directly within the RAS Mapper tool to also match it to the gauge data, depending on what you have available. If it's just time stage information or maybe velocity as well from direct measurements, you can query your data and your model to validate whether or not your model is replicating that observed data.
Yep. The last question from Wahid, and then we'll move straight on, that there is a ton more coming in behind at the moment, and Mozam Rind is hand up there, Joel, so we are aware that we've got another question on screen in a moment. But the last question from Wahid, we calibrate our hydrodynamic models for alluvial rivers and such channels using one-time readings. But after every flood event, the morphology and alignment changes significantly. So what should we do to make more sophistications in order to ensure the accuracy? Who wants to grab that one, Bob or Mark? Krey?
I'll talk about just briefly about sediment transport routines.
Let's keep them short though, because we're going to need to move on.
You can run sediment transport in HEC-RAS, but it's only going to be in the 1D interface. It's going to be much easier to do in steady or quasi unsteady flow. Trying to run a full unsteady flow sediment transport model, is very complex. So it can be done. You can simulate these things, but without calibration data, if you don't have data to calibrate to, your sediment transport model is not going to be worth anything. So certainly can be done, and we have an entire 3-day sediment transport course that explains that. But it's it is a very complex mechanism, and it's a bit chaotic, meaning sensitive dependence on initial conditions. You change one parameter in your model, and you can change the results. Therefore, you need to calibrate anything that's running sediment transport.
RAS 5 also has the capability of predicting channel bank erosion as well. So that's something we can address in the course as well.
Yep, that's great. There was one here from Dr. Sher Khan in New Zealand. Thanks for the great effort. Could you please advise a simple way to edit DEM? For example, cutting roads from the DEM.
Yeah, and I think that goes back to that first question that we had, and that will be through the process called terrain lifting.
Yep.
So yeah, go ahead and just, if you Google HEC-RAS blog, then type in terrain lifting. It'll walk you through an exercise in how to do that. It's actually very straightforward. You put a roadway in. I can do a roadway, put a roadway in my model in about 5-10 minutes. It goes very quickly.
That's great news. All right, then let's go straight to then. I think it's Pakistan. Looking at the flag behind you, Mazum, it's very good and very clear. So over to you. Thank you. And nice and slow with your question.
Yeah, thank you. I just want to add the comment that related to the DEM, that we don't have a very good quality DEM here in Pakistan. Like, we have only 30 by 30 meter resolution DEM. So we have tried to extract the geometry by ourselves, but it is not coming very up to the mark. So what we can do with that one, because we don't have any cross-section in the lower side of the country like in Delta. We are working on Delta, and there is no perfect DEM for that one. So what we can do is, anyone who can suggest something?
Anybody want to go? Bob, want to have a go at it?
I think that's another one for you guys, really, the 2D DEM.
Okay, well, what I would say about that is, again, your model is going to be only as good as your data coming into it. And if you don't have good data, you're not going to have a good model. And I tell my courses, sometimes I used to teach surveying courses and things like that, I can get better results if I go out with a hand level and a rod and a tape measure and Manning's equation on my calculator. I can go out and get better results for you than with $100,000 worth of LiDAR data if that LiDAR data missed the low flow channel. So you have to have the terrain incorporated. If you don't have the terrain, you're gonna have to get it in there, and you have to get good survey data. It can, and that's, I think, one valid question that comes up is, when would you ever go back to 1D if you had a good 2D terrain model? And in general, you wouldn't. You would go back to 1D if you didn't have good terrain data and cross sections that you could extract from the terrain data. You would need to just go back and manually build yourself a model. And sometimes you can do a fine job with that just using cross-sectional surveys. Again, just the relative elevations, but your output's only going to be as good as your input.
Yep. Okay, we'll keep going. Donald from Germany asks, with the 2D modeling, there are limitations with regards to how to input internal boundary conditions. Any tips? Does that make sense?
Yes, you cannot currently do that. And Mark, maybe you've got some other tips. I came up with a way using wormhole culverts to do that, to introduce a boundary condition, but it's a bit tough to do. You can actually throw flow anywhere into your model that you would like, but you have to, it's a trial and error method. So go to the website, surfacewater.biz, look up wormhole culverts, and you'll see a way to use those to introduce an internal boundary condition. Mark, hopefully you've heard of maybe in 5.1 they'll allow you to do that, because right now you can only bring flow in along the external boundary of a 2D area as far as I'm concerned. Do you know differently, Mark?
That's a limitation right now. The internal boundary conditions, you can insert a variety of different types of internal boundary conditions into your 2D domain that can include culverts, gates. You can also include a dam as an internal boundary condition, and also fail it, do the dam failure or levee failure as an internal boundary condition. With regard to culverts, long culverts that go from one portion of the domain to another, that wormhole concept is the limitation right now that Krey is referring to. Version 5.1 will have the ability to insert a long culvert into the domain that specifies an entrance location and an exit location, and then it'll attach to the associated grid. That will allow you to bring water from the external edge of the domain to an interior point of the domain. Right now, there are limitations with that. You can add hydrographs at any point along the exterior boundary of your 2D domain that you wish.
We'll keep going. How should we decide where to use 1D and where to invoke 2D? That's a classic, I guess, question.
Bob, you want to take that one?
Well, that is a classic question. I mean, I think we've all got comments on this, but I would say straight away. Firstly, it depends how good your calibration data is. Depends how good your terrain data is, and I'd make the point that one thing that was mentioned earlier was about very flat terrain, and you've got to be very careful with your terrain data if it's very, very flat, because you don't have a lot of error to work with in terms of where the water's going to go in a significant model. I think if you've got a general flow direction that you know, I would strongly suggest at least looking at a 1D model for that. You don't need a complex two-dimensional model if you don't have a lot of lateral flow, or over floodplains and then re-entry over stop banks rather, or levee banks, and then re-entry at different points. But even there, 1D models are pretty good. I mean, I broke my teeth on, that's a bad metaphor, but on 1D modeling going way back, and I would always use it in preference, simply because it is simpler. I'm not saying don't use 2D, by the way, but I'd let the other guys take up on that.
Yep. There's a ton of questions coming, so shall I keep? I think we'll move straight on. Similar vein is the question about, is a coupled 1D, 2D approach possible?
Anybody want to jump on that one? I will say yes, it's possible, and it's very complicated, meaning that you, because your 1D model cannot run dry, that's a current limitation of HEC-RAS, you have to introduce some flow, and it ends up being a bit more complicated to balance and get a stable model, because you have to have an unsteady 1D model. Now, looking at the poll results, most of those respondents said you would only run 1D steady flow. Now, you're going to need to be able to do unsteady flows to run 2D, and getting those to run even in 1D is why most people only went to steady flows, because getting those to run in 1D can be a bit excruciating to get rid of some of the errors. Any other thoughts on that, from Mark or Bob would be appreciated too.
Yeah, it does do a fully coupled solution. The same solver in RAS is doing both sets of computations for 1D and 2D. And the interface between the two will exchange water between both domains. But like Krey said, it is a little bit more challenging to set up, but it'll do a fully coupled solution.
The next one from Melbourne, Daniel is in Melbourne, CJ Arms Associates. That's good. When running 1D HEC-RAS models, the cross sections default to critical depth. Is there a way to help this model run better?
Well, they default to critical depth when it can't get a solution. I mean, the point out that I would make with 1D models is, if you start looking, it should be run as a mixed regime model, so that you've got both subcritical. So you need a downstream boundary condition and an upstream boundary condition for that case. Now, an awful lot of flood models, in fact, run as purely subcritical. Subcritical flow is very common, but if you start and run the model just as a subcritical model, and it starts then at the downstream boundary condition as a known condition, and the solution progresses or propagates upstream. If it comes to a cross section where it can't converge to a solution, then it defaults to critical depth and then keeps going. And if you see that in the output that you're getting, then the first thing I would do is to say, okay, let's run this as a mixed regime model with a boundary condition at the upstream end as well. And if you run it like that, then it will, in fact, pick up the change from subcritical to supercritical. It'll locate your hydraulic jumps and so on. Yep. That's certainly one area where you would get it defaulting to critical depth.
I've got a question here from Josh Cumberland in New Zealand, Otago Regional Council. And Josh says, should the 2D computation interval satisfy a general guideline that the computation interval should be equal to or less than the time it takes water to travel from one cell to the next? How do you balance manageable runtime to achieve this? Did I do that question too quickly?
No, that's a very valid question, because that comes up all the time. There is one equation that we need to make sure that everybody's able to solve before figuring out what you're doing in HEC-RAS 2D, and that's the Courant number. And that does imply some relationship between the velocities, the time steps, and the grid sizes. But again, it's not just the velocity, it's the speed of the information through the water. So it's the velocity of the water plus the propagation of a wave celerity through that water. And yes, what you're trying to avoid is having HEC-RAS run a computation and then skip over 10, 20, 30 grid cells with the water before it does another computation. It won't be able to keep up with itself. And when you plot the profile, you will see water stacking up in unrealistic heights, even if you get a model that runs with a beautiful animation. So yes, you absolutely have to balance your Courant numbers and figure out what your velocities are and your grid sizes relative to the time step before you even set your time step. And that's why in our courses, we take an hour or two just devoted to the Courant number and the derivation of that and troubleshooting to make sure we've got that time step nailed down correctly. Mark, any comments on that?
Well, one key additional distinction to that is that there are two solvers within RAS. One is a diffusion wave solver, which will allow you to use a Courant number of 2, and then the full dynamic solution is a Courant number of 1. So the question was very correctly stated, that you're really looking for in the full momentum solution, water should not cross more than one grid cell in a single time step. So you're looking at the portion of your domain where your highest velocities occur and your smallest grid cell resides to determine what that time step is. There'll be improvements to how it's handling the time step in version 5.1 as well. And we'll talk about that in the class also.
Next one is, does HEC-RAS 2D 5.0 have the ability to input a hydrograph at any location? For example, the location of a pipe outlet within the internal region of the 2D mesh, similar to that of 2Flow.
Yeah, that's right now a limitation. As Mark mentioned before, introducing an internal boundary condition can be done in some manner with structures, but trying to pull flow in, as in 2Flow, where you can put it in as an SA area anywhere you want to introduce it, that at present can't be done, which makes it very tough to calibrate to hydrological models where you need to reset your hydrograph at a given point in the model. It can be done, and I've done it with a pipeline on an example of the wormhole culverts. Again, just download that from the website. But I don't know, Mark, you might have some better solutions on that. But I don't know of any realistic ways of introducing, taking a tributary inflow, for example, in the middle of your 2D model and introducing it at that point rather than from the edge.
Yeah, it's typically because there's a pipe in the system, and you're trying to capture that flow that's exiting a pipe that's somewhere in the interior region of your 2D domain. So that right now the wormhole concept is the way you potentially do that, is you'd have to set up a connection somewhere at the outer edge of your domain, add a culvert with the wormhole concept, and have it discharge at the point of interest. With 5.1, you'll have the ability to use the same sort of long culvert concept in order to introduce an interior boundary condition. But right now, it's not a simple matter of just simply adding an interior boundary at a specific location to your domain. That's not available currently. But there are ways to get around that.
Yep, thanks for that. We've got about 10 minutes left, and we are still inundated with over a dozen questions here, and they're still coming in. But let me just go straight to this question from Jose Torres in Lima, in Peru. Hi, everyone. Thanks for the webinar. Could you give advice about modeling a flood simulation on a straight river, a plan view, flowing through a city? Give advice.
Urban, have you done that? Yeah, urban is an interesting context. Mark, because you've got some of those ones that ran through some urban settings, maybe you want to cover that one.
Yeah, we've done a number of urban settings with riverine conditions, and urban settings are unique because of the buildings. And typically in the past, we've just bumped up the roughness to account for the interference of the buildings, which is a very approximate way to handle an urban setting. The models we've been using in urban settings with RAS 2D or combined 1D 2D solution, we've actually incorporated the buildings into the domain. so that the model actually sees the interference of the building and captures the flow going around the building, and also eddies behind the building. So all the hydrodynamics that are created by the building itself can be properly captured. So in an urban setting, it has to be set up very carefully. Urban settings usually have pressure flow bridges, and as Robert was talking about, you have to model those pressure flow bridges with a 1D domain, so that requires that linkage between the 1D and 2D.
Yep. And one point of warning in that one is not to double count your roughness. If you're using a roughness that's supposed to account for the buildings, and then you've extracted them out of your LiDAR data and put it into the terrain, you're double counting, so watch out.
Yep.
Yeah, so in that case, the flow around the buildings would be in the street, so your roughness would now be reduced down to a typical roughness value for your street.
Yep. A quick one now. Sorry.
I'll just very quickly make the point that in one-dimensional modelling through an urban area, you would normally have if you've got a substantial building, you'd have a cross-section at each end of the building in the flow direction, and you would simply use the block area method at each of those cross sections to simulate the location of the building. But then you've got an issue with assigning Manning's end upstream and downstream, and that's something that's covered in the full course as well, as to how we deal with the fact that data is entered section by section, but calculations are made reach by reach, and that imposes some interesting comments, which we'll come to eventually with the
that's right. Yep.
workshop. Yep.
In September in the Brisbane course. It's a quick one now. When is 5.1 expected to be released?
Well, that's always anybody's guess. Right now, what I was told by Gary Brunner, who leads the HEC-RAS team, is that they're hoping to have 5.1 out somewhere around the beginning of the next calendar year. As we've always seen, these dates tend to slip as they're working through bug issues and that sort of thing. But that's the current goal.
I never make any promises about release dates.
That's all right. That's all right. John Single in Townsville says, at present, is the assumption that coupling 1D and 2D, 1D and 2D components in HEC-RAS not available?
It is available, and it's one of the demo models. You can download the demo models from HEC-RAS, and it actually includes a coupled model. So yeah, it's very much available. It's one of the main features of it. Yes.
No worries.
We use it frequently.
Yep, sure. Andre Conca from Italy, can you suggest a method in 2D to avoid pits formation during the flooding process, like levees in 1D? Raise the terrain, question mark?
Yes.
Yes. Anonymous viewer. Does HEC-RAS have parameters to account for snowmelt runoff?
No, that would have to be done independently and input as your hydrograph entered at your boundary as your part of your boundary condition. So you compute that with something like HMS or another software.
Steve Ratcliffe in Tasmania, how stable are 1D/2D linkages in HEC-RAS? I've used IS-2D and found it unstable at times, requiring the addition of high Manning's buffers to stabilize the model or large numbers of cross sections.
Yeah, that's something you got to watch out for. 1D, 2D interfaces should only be set at areas where the 2D model has reverted back to one-dimensional characteristic flow. So if you're trying to balance the flow, if you have a 2D model and you want to put a 1D reach in it, but that model has super elevation accounted for in the 2D section, and you try to put a cross section there, well, by definition, HEC-RAS's 1D cross sections are absolutely flat across the top, and it will go unstable. So as long as you stabilize it or set your connections to be in areas that are inherently 1D in nature, then you have pretty good success. But if you try and merge them together, you will have some massive instabilities. In some cases, you can get beautiful animations again, but when you look at them in profile and section view, you'll realize that there were a lot of instabilities that just got pushed right through the model.
I would clarify, you can usually get those instabilities worked out with the choice of those roughness values along that lateral structure between the 1D and 2D. Do need to consider what type of interface that is. If your flow is crossing natural terrain, you're going to have to adjust those roughness values down low. If you're using the Weir equation as that interface, but RAS also has the ability to use the two-dimensional equations instead of the Weir equation at that interface, which allows a more stable solution. And because it is a fully coupled solution using the same computational engine, those handoffs are also pretty stable with RAS. We've done a couple models, so they are a little bit more challenging to stabilize, but very, you can work through the stability issues, and there's some guidance on that.
Okay, Siash Joshi in New Zealand says, does the 1D section need to be extended in the 2D area while doing a 1D, 2D coupled model? No. No, those two domains need to be juxtaposed, but never overlap. Otherwise, you're double counting the conveyance. Second question from Dr. Shirkan. Could we exclude an area from the mesh instead of having more than one SA/2D areas?
I don't know of a way to just exclude an area. Mark, do you know of a way to do that, to just say this area, just to cut it out? You can't have any donuts.
You can't have any donuts. You can't have any holes in the domain. If it's because it's an obstruction, you can also do an override polygon within your geometry to give it a very high roughness value so that it's not conveying water through that space.
But it will store water in that case, and volume would be accounted for. You can't block it out that way.
Or you can block it out by elevating that portion of the terrain,
raising
so that there is a true blockage at that location, like you would do with a building.
Next question from Sally Haywood. How would you suggest modelling a floodway through a vineyard? You like this question, Mark, after your visit to Barossa on the weekend. Would the solution just be increasing the roughness? And if so, are there any studies that could help this choice? Sally's from New Zealand. Yeah.
Mark, maybe this comes into depth varying roughness, and hopefully that will be introduced soon, but you might want to talk about that.
Yeah, right now it does not have the ability to do depth varied roughness. That is something that they are working on. So you'd select a value that you think is reasonable for the flow conditions you're trying to simulate, and then capturing all the features. So a vineyard might have berms around the outer edges or other features that are going to be important to capture, and that's where you use the mesh tool, the break line tool, to refine your mesh to pick up those features.
Great.
I think it also depends on how you're modeling it. If you're modeling it in 1D, then of course depth varying Manning's N is available for you. There's also plenty of studies available on the effect of significant vegetation on Manning's N values. There's plenty of information in the literature on flow through forests, on flow through vineyards as well, and the appropriate values of Manning's N can be found by looking at some of that material.
We've got a question here from Nivesh in Kathmandu University, Nepal. Hello, everyone. I've used HEC HMS 4.2 and found it to be kind of unstable. The entered data would go missing. Are there any such issues with HEC-RAS?
I'd say I don't know, Mark, you might have your own comments. The most frustrating issue, the most common little glitch is that your terrain disappears and you have to try and get it back. But I haven't had data disappear, but 90% of the time the errors that show up in HEC-RAS, by saving, closing, exiting, and coming back in, 90% of the time those errors can go away. But I haven't had data just disappear.
No, I haven't either. I know what challenge he's talking about with HMS. I've run into that too, but I have not run into similar problems with RAS.
Well, there's 3 questions here. Maybe we'll knock them over and then we'll call it a day, I reckon. Which other modeling tools have similar features like HEC-RAS? What would you recommend?
Well, I would say go to the UK Environment Agency website and go to your 2D benchmarking. Just type in 2D benchmarking and you'll see the whole study. And then Gary Bruner has published his own to show how it compares against that. That's probably the most comprehensive study, unless Mark or Bob, you know of others.
Yep.
Yeah, one of the things that's key about that study that will show you some of the differences between the tools is not all 2D models are the same in terms of the portions of the equation set that it's solving. Some of them are more of a diffusion wave solution. Some are using all the terms in the St. Venant equation, but not all of them are. Yep. So they may not compare exactly the same in terms of capabilities.
Last couple of questions. Wahid has asked these last 2 questions. Is it possible, Wahid's in Pakistan, is it possible to run more than one computational domain, one inside each other, 2 simultaneous dam breaches, as using connections requires weirs at the interface?
Mark, you want to go with that, or Bob?
Not sure I understand the question.
Is it possible to run more than one computational domain?
Well,
one
yeah, I
inside
think
each other?
one inside each other, that can be done in two-flow by coupling the entire thing. Again, we cannot have donuts. When you can have many storage areas and 2D areas all in the same model, and they can all talk to each other across an interface, but you cannot put one within another. What's nice about the break line feature is you can go in and you can assign a break line and make it a nice pattern over your model and put a really fine resolution grid in the middle of your model. And that might come, that's generally the reason people do that in two-flow. You have a coarse grid on the outside, a fine grid on the inside. You can get around that with break lines and just make a shape file out of your break lines.
The simultaneous dam breach, if what he's referring to is doing a cascade breach, where one breach of one dam, that outflow from the breach arrives in the reservoir for another downstream reservoir, and then you do a simultaneous breach of that reservoir. That's something that you definitely can do, and we have done. We've actually done it on the 4 largest reservoirs in the center of the U.S. On the Missouri River, doing that cascade breach. That's a function that works very well within RAS.
Look, gentlemen, and everyone listening and viewers, look, really appreciate you staying with us today. It's been fantastic. We're going to close off now. I noticed this last comment from Wahid. Thanks to everybody at IceForm. Please make more possibilities in the future, and we definitely will. Don't forget the training course coming up in Brisbane. I've noted that on the screen here. We'd like your feedback. There'll be a recording, and we'll email that to everybody. Stand by for an email from us. But particularly think about this course in Brisbane in September. You can come to any one of the 5 days that are being run at different levels of HEC-RAS. There's 4 free webinars coming up there, of course. And I see your comment, Dr. Sher, just now coming in. Is there any training courses in New Zealand? Haven't planned for it yet, but let's email each other and have a chat about that. I'd like to do that. Well, I think we're there, and look, thanks very much for everybody for staying with us. We look forward to seeing you at another webinar, of course, coming up that IceForm runs. All the best for now.
Thank you.
Thank you.
Thanks.